2020, which was awarded to Hillel Furstenberg from the Hebrew University of Jerusalem, and Gregory Margulis from Yale University, United States. We are very lucky that we found two eminent specialists and long-term collaborators of the respective Abel Prize winners who will explain their work to you tonight. Professor Benjamin Weiss, also from the Hebrew University of Jerusalem, Israel, will introduce the work of Furstenberg, and Professor Manfred Einsiedler from ETH Zurich will introduce you to Margulis' work. My name is Frank Redig. I'm a probabilist at the Delft Institute of Applied Mathematics, and I will provide you with a short introduction to our evening. I am going to start with the image of a bridge, which you see here already. Let me explain why. The Abel Prize 2020 was awarded for pioneering use of probability and dynamics in group theory, number theory, and combinatorics. Both prize winners have built unexpected and deep connections between ergodic theory, which is an area of mathematics, and other areas of mathematics, including number theory, combinatorics, Lie theory, group theory, and graph theory. This area of ergodic theory, which you will hear more about tonight, including also what it englobes exactly, has at first sight no connection with the other mentioned areas. But in mathematics, a second and a third sight are often needed and useful. And then things which seem unrelated suddenly become actually related. By building these unexpected connections, the Abel Prize winners were able to solve deep problems in the areas they were connecting to, such as number theory, and create a formalism of extraordinary fertility. For instance, one of the spectacular fruits of this methodology of Furstenberg is the celebrated theorem by Green and Tau from 2004, stating that the sequence of prime numbers contains infinitely many arithmetic progressions of any length. The proof is using Furstenberg's ideas connecting ergodic theory with number theory and additive combinatorics. So what you see here in the picture is a sequence of primes, and the difference between two successive ones is always 210. And so the theorem tells that there are infinitely many such progressions of any length. And I think now the biggest that is found experimentally is 27. Dr. Charlene Kalle from Leiden University will explain you in more detail what is ergodic theory. But let me give a short introduction to that introduction. As is the case for many areas of mathematics, the origin of ergodic theory lies actually in physics, more precisely in foundational issues of statistical mechanics. Boltzmann formulated a hypothesis which he called the ergodic hypothesis in 1870. Statistical mechanics is the area of physics where one is interested in how the macro world emerges from the micro world. For instance, how from the chaotic motion of colliding molecules, laws of thermodynamics, like for instance the ideal gas law, follows. And Boltzmann was the first to introduce actually probabilistic concept in physics, which at that time of Newtonian determinism was very original. The word ergodic was coined by Boltzmann, who knew Greek very well, and thought carefully about the choice of the word and the concept he wanted to introduce. It stems from ergon, which means work, and hodos, which means path. And the combination ergodic refers to paths of constant energy, referring to the conservation of energy in mechanical motion. So the so-called ergodic hypothesis of Boltzmann, as formulated by Ehrenfest in his 1911 book, so here is Ehrenfest, who probably is teaching at this moment at Leiden University about Boltzmann's ergodic hypothesis, maybe, could be the case. This hypothesis in Ehrenfest language states that for long times, the fraction of time a mechanical system spends in a region of phase space is proportional to the phase space volume. So this possibility of replacing long time averages by phase space averages is one of the foundational ideas of statistical mechanics. After Boltzmann, mathematicians started to work on these problems and everything became clear, as usual when mathematicians enter the game. In particular, hypothesis became theory. These mathematicians created the area nowadays known as ergodic theory. The pioneers of that area are George Birkhoff, which you see on the left, and John von Neumann, which you see on the right. And as you see, Birkhoff was a bit taller than von Neumann. And I have also a little phrase added of von Neumann that tells you that if people do not believe that mathematics is simple, it is only because they do not realize how complicated life is. So after these foundational works, ergodic theory became an independent and mature area of mathematics with natural and strong connections to probability and dynamical systems, but as we already mentioned, with many fruitful, unexpected connections as well. Charlene Kalle will tell you more about that tonight in her introduction. So let me conclude by giving you a short overview of the rest of the evening, coming back to the bridge picture, making the bridge to the rest of the program. First, Dr. Charlene Kalle from Redig University will provide a 10 minutes introduction to ergodic theory. Second, Professor Benjamin Weiss will introduce you to the work of Hillel Furstenberg, of whom he is a long-term colleague, collaborator, and friend. And third, Professor Manfred Einsiedler from ETH Zurich will introduce you to the work of Gregory Margulis, of which he is also a long-term collaborator and friend. After the talks, there is time for discussion question session, which will be moderated by Professor Hollander and Evgeny Verbitsky from Leiden. Please post your questions in the Q&A chat at any moment you like. It remains for me to wish you an inspiring evening. And now I give the virtual floor to our first speaker, Charlene Kalle.
Thank you very much, Frank. So now I have to press some buttons. So let me try and get everything set up. Okay. So thank you very much. So as Frank already mentioned, ergodic theory as a scientific area originated from Boltzmann's work in physics. And the purpose of this talk is to tell you a little bit about how ergodic theory came to be a prominent area in mathematics that has led to many prizes and awards in the past decades. And the last two Abel Prizes are only the newest great additions to this list. So for this, we go back to the work of the Ehrenfests. So you see the couple, Tatjana Ehrenfest-Afanasieva and Paul Ehrenfest here in the top corner. So in 1911, they published a joint book together, their famous book called The Conceptual Foundations of the Statistical Approach to Mechanics. And in this book, they presented Boltzmann's theories as one coherent story. And central to Boltzmann's work, they placed what they call the ergodic hypothesis, which stated very briefly is the following statement: an isolated mechanical system in equilibrium eventually passes through every dynamical state compatible with the assumed total energy of the system. And the consequence of that is what Frank already mentioned, the short statement time average equals space average, which he phrased as it says on the slide. So it's very nice to be able to start with the Ehrenfests on this evening, since they have a very strong Dutch connection. So in 1912, they moved to the Netherlands, where Paul Ehrenfest took on the professorship in theoretical physics at what was then still called the Rijksuniversiteit Leiden. And in 1990, he became a member of the KNAW, who is obviously organizing this nice event tonight. So the Ehrenfest put this ergodic hypothesis central to Boltzmann's ideas. But from the beginning, there were doubts about whether this was the right condition to set. And also Boltzmann himself had doubts. And he actually never put the condition down in such explicit words himself. That this condition was actually too strict became indisputably clear in 1913, when mathematicians Arthur Rosenthal and Michel Plancharel independently showed that any realistic gas model cannot satisfy it. So from that moment on, people went to search for conditions under which the statement time average equals space average is actually true. And it took a while before a positive mathematical answer came, but this happened eventually in 1931. So in that year, not one, but two ergodic theorems emerged. And the first one was announced by John von Neumann, who we see here on the top left. I think it's left for everyone. Well, John von Neumann is famous for many things, maybe most notably for his involvement in the development of the atomic bomb. He publicly announced his version of the ergodic theorem, including the proof, in the summer of 1931. And then in the autumn, Birkhoff, who is in the top right corner, he managed to also finish his version, and he also managed to get it published in the same year, even before von Neumann's first result got published. So what do these theorems say? Well, basically, they just give the right mathematical conditions under which the statement time average equals space average is justified. And briefly put, we need two conditions, which are here on the slide. So the first one says that you need to be able to put some stationary probability distribution on the state space, which means a probability distribution on all the possible states that stays invariant under the time evolution. And secondly, the system needs to be irreducible in some sense, which is less strong than how how Boltzmann phrased it. So you need to have, you need to not be able to decompose or split the system into several parts on which you can independently study the dynamics. And in that case, if we observe the system through some sort of observable, then we have that the time average of that observable along a single trajectory of the system converges over time to its average value over the whole state space, which is the space average of that observable. So the theorems of von Neumann and Birkhoff, they're similar, but also different. And the main difference lies in the way that this convergence is obtained. So what convergence means in this last statement. So their results that gave this thorough definition of the ergodic theorem, so an actual theorem, started the development of ergodic theory as an independent mathematical research area. As Frank already mentioned, later it became clear that ergodic theory also had a lot to offer for other areas of mathematics. And we will hear, well, a lot about that in the next two talks. So here I would just like to mention one small example of an unexpected statement that ergodic theory can give. And this is related to Benford's law, or actually more accurately, Newcomb-Benford's law. In 1881, scientist Simon Newcomb, he was an astrophysicist and a mathematician. So he noticed that in books containing logarithmic tables, the pages showing the conversion of numbers having first decimal digit equal to 1 were more used than the other pages. And also he noticed that the higher the first decimal digit of a number was, or the numbers on the page was, the less used these pages became. So he concluded that apparently not all numbers or not all decimal digits occur equally often in as first digit of numbers. So in 1937, the physicist Frank Benford went one step further, and he analyzed several large numerical data sets and computed the frequency with which every digit occurred in these sets as a first digit. So what is interesting about what he did is that he considered all sorts of different data sets that have no obvious common features. So he looked, for example, at lists of weights of molecules, population sizes, an address list, or just the numbers that occurred on the cover of one newspaper, the complete cover. And then he found the percentages of digits that you see here on the slide. So in all of these situations, so the numbers here are sort of averages he took from all these observations, but he noticed that approximately 30% of the time, the first digit of these numbers was a 1, and then these percentages decrease as you see here on the slide. And these results together, they are now summarized in what's called the Newcomb-Benford law. And the surprising fact is that also powers of 2 obey this law. And this is what we see here. So on the top of the slide, you see the sequence of powers of 2. So we have 1, 2, 4, 8, 16, 32, etc. The first digits of these numbers we see below. So 1, 2, 4, 8, 1, 3, 6, 1, 2, 5, etc. And then you could wonder what the frequency of, for example, the digit 1 is in this bottom sequence. And then it turns out that one can rephrase this question into a dynamical setting and then use the ergodic theorem to compute these frequencies. So the way to do that, obviously I won't spend time on the details, but for example, if you want to compute the digit 1 or the frequency with which the digit 1 occurs as a first digit of in this sequence, then this happens precisely if the number 2 to the n, so the digit 1 is the first digit of a number 2 to the n, precisely when the fractional part of the number n times log 2 lies between 0 and log 2. And with fractional part, this means the part after the decimal point. So if you want to compute the frequency of the digit 1 as a first digit, then we need to observe, so this is our observable, how often these fractional part of n log 2, if you vary it over all n's, lies in the area between 0 and log 2. So here you see sort of our dynamics and our time average emerging. So you follow this sequence step by step when you increase n. It's like a trajectory of a dynamical system. And you observe when the sequence or how often the sequence lies between 0 and log 2. And then according to the ergodic theorem, this frequency will be equal to the size of the area that we consider, and that is the area between 0 and log 2. And the size of that area is precisely log 2, which is 0.301. And there you have our 30%. So for the other digits, you can, for example, take, for the digit 2, you take log 3, you observe when these values lie between log 2 and log 3, and the area of that interval is 0.176. And so you can, in the same way, you can compute all possible frequencies. And here at the bottom of the slide, you see the frequencies you get for the powers of 2, and then below that, the frequencies observed by Newcomb and Benford, and you see that they're actually quite similar. So yeah, this is just one short example of how you can, what the type of statements you can unexpectedly get from ergodic theory. And that brings me to the end of my talk. So shall I stop sharing? I'm not sure. Okay, Frank is back.
Yeah, so please, Benjamin, can I give you the virtual floor for the next talk?
Okay, so until when should I be speaking?
You have 30 minutes.
30 minutes, okay. Okay. Having problems with the share screen again. So Okay. Okay, so thank you. I'm sorry, this flips back and forth. Can you hear me? Am I unmuted?
We can hear you very well.
Okay. So thank you for this invitation. I was told by Evgeny when he asked me to speak about the work of Hillel Furstenberg that the audience would include many non-mathematicians. And that's the kind of talk that I prepared. It's not a talk aimed at mathematicians. And so the experts for whom what I'm going to say is well known or trivial will have to forgive me. On the other hand, I learned long ago that you should not underestimate the pleasure people get in hearing things they already know. People go to concerts and listen to music, which they've heard many times. And so with that, I'll begin. And I thought that I would spend the first few minutes giving you a brief summary of the life of Hillel Furstenberg, because that's something everybody can follow easily. And it's like all lives, every person is unique, and his life was unique as well. And so I'm going to begin by giving a brief summary of his brief biography of his life. And I should also thank the Königliche, the KNAW, for asking me a few months ago to write an article about his life and work. And so the preparation for this talk was quite a bit easier. So Hillel was born in 1935 in Berlin. You can read as well as I can, I hope. And I'll go through this quickly. His family escaped soon after the Kristallnacht pogrom in November 1938. Their first stop was in England. His father took sick there, had to have an operation, and he passed away. And he arrived with his mother and older sister in the United States in 1940. For a year, they lived with an uncle who had a poultry farm in New Jersey. Then they moved to New York City. And his high school and college studies were at the Yeshiva University complex, where I also studied. While still in high school, his mathematical abilities became evident. He was greatly encouraged and supported by Yekutiel Ginsburg, the founding editor of the Scripta Mathematica, which was at the time a very serious journal in the history of math and recreational math. Well-known mathematicians like Coxeter were also part of the editorial board and published papers there. And Yekutiel helped him by employing him when he was at the college, connected with the journal, including translating articles. Okay. He graduated in 1955 with 2 simultaneous degrees. He went to Princeton. His PhD advisor was Bochner, and he got his PhD in 1958. Then he was at Princeton, at MIT. He got a position at Minnesota, and he was a visiting professor at Princeton in 1963-64. When I was a graduate student at Princeton, I already knew him in some sense. I knew his wife, and he had been a classmate of my older brother. And in Princeton, I became his student. I took a course in probability theory with him. And the last month of the course were devoted to some new concept he had invented that he called at that time absolute independence. And for the experts, this is what evolved a few years later into the notion of disjointness, which I'll say a few words about later on. He returned to Minnesota. He got tenure as a full professor. In 1965, he accepted an offer from the Hebrew University, and he remained his academic home until today. He supervised many students. Many of them became quite prominent. Most have remained in Israel. And he is to a large extent responsible for Israel's becoming a leading center in ergodic theory, topological dynamics. He won more prizes that you can see here. I haven't listed all of them, but I think that's enough. Now we come to the Abel Prize. So in the press release for the Abel Prize, as you've already heard, it was awarded to Hillel Furstenberg and Gregory Margulis for pioneering the use of methods from probability and dynamics in group theory, number theory, and combinatorics. Now, to give you some idea of what Hillel achieved, I will go into a tiny bit of history of probability theory in the 20th century. In 1900, the great mathematician David Hilbert formulated 23 problems, which set the course for a great deal of mathematical work during the 20th and 21st century. His sixth problem was, the investigations on the foundations of geometry suggest the problem to treat in the same manner by means of axioms those physical sciences in which mathematics plays an important role. In the first rank are the theory of probabilities and mechanics. What you see here in Hilbert's formulation is that for Hilbert in 1900, it's not that probability wasn't being used in physics. Probability was a part of physics. It became a part of mathematics only in the first decades of the 20th century due to the work of many people, which I'm not going to, this is the continuation of Hilbert's formulation of the problem. As to the axioms of the theory of probability, it seems to me desirable that their logical investigation should be accompanied by a rigorous and satisfactory development of the method of mean values in mathematical physics, in particular, the kinetic theory of gases. So when Hillel began his career more than 60 years ago, probability theory was far from the center stage in the mathematical community. He turned it into an important tool to solve outstanding problems in diverse areas. I will concentrate my talk, most of my talk, on just one topic. The way we learned when we were young. Whoops, how do I go back? I go back. Sorry, I'm a bit of a dinosaur. I have some trouble with this mechanics of this. He has made contributions. I was asked to speak about his contributions, but I think it's enlightening if I explain one of his very first papers written while he was still an undergraduate. And again, I had in mind really non-mathematicians. And so now I'm going to talk a little bit about pure mathematics, which won't, so I get right to the primes, which you've already heard about. I didn't know that so many people before me, actually 2 people before me, will be giving me such a good introduction. Prime number P is one that has no divisor other than 1 or P, like 3, 5, 7, 11, 13. And there's a well-known joke for an engineer who sees 3, 5, 7, 11, 13. Well, all odd numbers are prime. 9, oh, that's an experimental error. But not 6, 15, or 39. One of the first mathematical theorems was a theorem of Euclid in his Foundations of Geometry, Elements of Geometry, and he showed there were infinitely many primes. Just means no matter how large a number you think of, there's a prime bigger than it. Since Euclid's time, many proofs of this result have been given. In 1955, Hillel published a completely new proof in a short article that took up less than a page. Here's the proof. It relies on the geometric idea of a topological space, which I won't explain, and the notion of arithmetic progressions, which you've already heard of. Hillel's novel idea was to endow the integers with the structure of a topological space as follows. Take for a base for the topology all arithmetic progressions. In this topology, each arithmetic progression is both closed and open. Now assume the set of primes is finite. Denote by AP all multiples of P. These are arithmetic progressions, and there are only finitely many, and the finite union of closed sets is closed. But the complement consists of just 2 points. And this clearly can't be open because an open set has to contain a neighborhood. You would have to have some arithmetic progression which contains 1 and minus 1. You've seen a complete proof. Erdős believed that up above there was a book which contained the most elegant proof. Some years ago, Martin Eigner and Günther Ziegler wrote a book titled Proof from the Book, dedicated to Paul Erdős. In the book, you'll find this above proof by Hillel published when he was 20 years old. One of the reasons I exposed this proof is that in his PhD thesis, which was published in 1960, he endowed the integers with the structure of a probability space, and he turned it into a dynamical system. And this is one of his very key fruitful ideas, which we will encounter pretty soon when I describe one of his achievements. So to describe the achievement, here is a Dutch connection. Actually, there will be 2 Dutch connections in what comes next. There's a well-known theorem of Van der Waerden, which the probabilist Ginshin included in what he called 3 pearls of number theory. So here's the definition of arithmetic progression. You see the example, it's just what you learn in school. And Van der Waerden published a paper when he was quite young called Bewijs einer Baudetschen Vermutung, proof of a conjecture or assumption of Baudet. Baudet was a very young Dutch mathematician who actually passed away several years before this paper was published. And before I formulate the theorem, I should also point out that the conjecture was actually made by Isai Schur, but let me get to the theorem. If you divide the integers into a finite number of classes, C, at least one of these classes contains arithmetic progressions of arbitrary length. This is the infinite formulation, and there's a finite formulation. If you fix the length of the arithmetic progression that you would like, and you fix the number of classes, C, you don't have to divide all the integers into C classes to be certain one of them contains an arithmetic progression of length K. It suffices to look at the integers up to some suitably large number M, which depends only on C and K. For example, the simplest non-trivial case, you would divide into 2 classes. You would look for an arithmetic progression of length 3, and it turns out that M equals 9 will suffice. As soon as the numbers from 1 to 9 are divided into 2 classes, one of them will contain an arithmetic progression of length, and here's a beautiful typo, of length 3, of course. And finally, for those who are being bored by what I'm saying, try to check this in the next few minutes instead of paying attention to these arcane things. Now, it's natural to ask, can you say which of the classes contains these arithmetic progressions? Now, you observe that if there are 10 classes, at least one of them contains 1/10 of capital M. Remember, we're dividing the integers from 1 to m. If you divide them into 10 classes, at least one of them contains 1/10. This simple observation motivated Redig and Turan to the conjecture that for any constant, no matter how small, and any k, no matter how large, there is some finite m, so that if a subset of the integers from 1 to m contains at least epsilon m elements, then that class must contain an arithmetic progression of length k. This conjecture was the first non-trivial case was proved by Roth using quite elaborate techniques from analytic number theory in 1953. Then, more than 20 years later, Redig, who won the Abel Prize in 2012, established the general case via a very involved combinatorial proof. In that year, in 75, Konrad Jakobs, who was one of the giants of ergodic theory in Germany in the post-war years, came to Jerusalem and gave a talk at the colloquium, and he expounded this theorem of Redig. Hillel was in the audience, and what Hillel realized very quickly is that this arithmetic result is a generalization of what's probably the first fundamental result in ergodic theory. I say here dynamical systems, long before the Ehrenfests formulated, not long, but at least 15, 20 years before the Ehrenfests formulated their ergodic hypothese, Poincaré proved what is called the Poincaré recurrence theorem, which I won't formulate exactly, but informally it says that if you have a conservative system, this is what Charlene was saying, some probability measure is being preserved. For most points, the orbit under the time evolution will return arbitrarily close to the starting point, P0. So this is the first sentence on this slide is the theorem of Poincaré. Poincaré recurrence goes back to the 19th century. Hillel's generalization was to multiple recurrence. And all that means is that not only will there be times when the orbit comes back close to the starting point, but at times t and 2t and 3t and kt, the point will also return close to the original starting point. It was Hillel's realization that insight that this theorem, of this multiple recurrence theorem, is completely equivalent to the theorem of Redig, which was the proof of the conjecture of Redig and Turan. The advantage of this equivalent version is that now we have a great deal more structure. We have to prove a theorem which can be stated for all measure-preserving systems. Without going into a detailed definition of what these are, there are many kinds of such systems with quite different properties. At one extreme, there are almost periodic systems, which are exemplified by just rotating a circle. You just rotate the circle by any angle. At the other extreme are chaotic systems, with a great deal of randomness, or systems with some degree of randomness. For these extreme types, the multiple recurrence was not too difficult for Hillel Furstenberg, I should point out, to prove. In order to bridge the gap between them, Hillel established a general structure theorem in which, in great part, was parallel to another fantastic work of his that appeared in '63 on distal systems. This result on distal systems, this is an aside, was completely unexpected, ushered in a new area in topological dynamics, which is the topological version, in some sense, of ergodic theory. It all comes from classical dynamical systems. It's just a question of, oh, I went too quickly into that. It's just a question of what you abstract, whether just the measure or just the topology. Okay, so this we've gone through. And Hillel's pioneering paper ushered in a new era. His methods answered many questions that had baffled the best experts. His later work in this area, he collaborated very closely with Yitzhak Katznelson. They published a series of joint papers. Probably the most well-known is one in which they proved the density version of what's called the Hales-Jewett theorem, which I originally thought I would try to explain, but then I realized that it probably would be a little too complicated to explain in carefully. So I stuck to the Semerady theorem. And actually this, I was scooped on these few lines, the celebrated achievement of Green and Tau, who showed that the primes contain arbitrarily long arithmetic progressions, don't rely directly on the ergodic methods of Hillel, but in spirit, they follow a similar line. Actually, even before Green and Tau, Gowers gave a new proof of the Semerady theorem using harmonic analysis and introduced new analytic ideas. But in spirit, again, Gowers' proof is also very similar in spirit to Hillel's proof. Where am I going from here? Okay, I wanted to give a plug so that I promised just one thing, but I couldn't resist mentioning his paper, which he published in '67, Disjointness in Ergodic Theory, Minimal Sets, a Problem in Diophantine Approximation. There's a legendary story, I can't verify it, that when the paper appeared, some experts thought that Furstenberg was a pseudonym because they couldn't believe that one person wrote such a paper. In conclusion, I think that not only did Hillel do an enormous amount on his own, but he nurtured generations of students who went on to great careers in mathematics, and I mentioned a few of his students. I count him as my teacher and have had the pleasure of being his colleague for many years at the Hebrew University. So, of course, I thank him as well. And I think that half an hour has passed, and I thank you for your attention.
Thank you very much for this very beautiful contribution, Benjamin, both highlighting history, mathematics, and even a proof. So thank you very much. I would like to give now the floor to Professor Manfred Einsiedler to highlight the work of Margulis. So
Yes, thank you. I'll just have to share my notes. Hopefully you see them now.
Yes, we see your slide. Yes.
Thank you. Good. So it's a great pleasure to be here and to give this talk on the work of Gregory Margulis. And as before, I want to emphasize that both of the prizes and also the prize for Margulis is really for building bridges. And as before, somehow one of the bridges that was built by Margulis and strengthened a lot in his work is connecting the two areas of dynamics and number theory. And I want to outline two examples of such a connection, and maybe in the end we have time for just a few more. Good. So the first theorem that I want to explain of Margulis is in the area of the Fenton approximation. And to sort of start the discussion, I want to really explain what the Fenton approximation is and what it amounts to, what the theory is about somehow. So I take a real number, alpha, think of pi or some other real number, square root 5. Then we can definitely approximate alpha by rational numbers. So by this, I just mean a fraction m over n, where m and n are integers, maybe with a sign. And of course, the denominator is not allowed to be 0. We don't want that. And of course, we can approximate every number by rational numbers because what is a real number? One definition would be to just say a real number is a decimal number that just may have infinitely many decimals after the comma. But of course, we can just stop at finitely many, and then we get a rational number. And then we don't get really the number that we're interested in, we just get an approximation. So for pi, this would be 3.1, which is of course 31 over 10. And here we have an error that is less than 10 to the minus 1. We can say pi is 3.14, then we have again a rational approximation, and this is 314 over 100. Here the error is less than 10 to the minus 2, or 1 over 100. And so on, of course. And somehow in this type of approximation, when you really use the finite decimal expansion to approximate the real number, you notice that the denominator, the 10 here, and the 10 to the minus 1, they always tend to be the same. Occasionally, maybe you can do a bit better in the approximation, but most of the time for pi, you will have that here you have 10 to the 4 in the denominator, and you get 10 to the minus 4 as the error of approximation, which is not so great, but in fact, one can do much better. And this is one of the earlier theorems in the theory of the Fenton approximation, which goes back to Dirichlet. Dirichlet showed that one can always find rational approximations m over n, where you estimate the error, alpha minus m over n. This is absolute value. It just means I throw away the sign. If the difference is negative, I throw away the sign. If it's positive, I just look at the difference, the error. And what we have here is that the approximation, the error, is actually, the error is smaller than 1 over n squared. So not only can we do 1 over n, which is what the decimal approximation does, we can even do 1 over n squared. And in the example of pi, this looks as follows. So if you take, for instance, 22 over 7 as an approximation, you see that, and you can type it into the calculator and find out that this approximation, 22 over 7, is actually much better. It's than you would expect, because the denominator is just 7, but the error is less than 1 over 100. If you go to the next one, of that type of approximation, 333 over 106, then the error is less than 10 to the minus 4, which is 1 over 10,000. And if you look at the next one, even 355 over 113, there's some kind of symmetry if you read it the right way, 113355. So it's actually a fraction that's easy to remember if you train yourself to remember that. Here you have an error which is less than 1 over a million, even though you just use a denominator 113. And this is precisely what Dirichlet says, that for any real number alpha, you can find rational approximations that are way better than you would expect. They're so good that the error is less than 1 over the denominator squared. Here the denominator is 113. So squaring that would be on the order of 10 to the minus 4, which is happening here. But occasionally this approximation is even much better. And here you get 1 over a million. So this is just to hint at what the Diophantine approximation is about. And of course, since then, many other generalizations and other questions have been discussed and have been solved to a large extent. And I want to highlight sort of one theorem in that direction of Professor Margulis. And for this, let me also point out somehow that this Dirichlet theorem, while it's great, sometimes it can't be improved, at least not much. So for certain real numbers, so I'm thinking here of the golden mean, for instance, or other numbers like square root 2, one cannot improve this statement by much. There may exist a constant. So for the golden mean, this is actually happening. There exists a constant, so that when you look at the error of the approximation, it's never better than this constant divided by n squared. So this constant is basically 1 over square root 5 in this example, maybe a little bit smaller than that. And in that sense, this theorem of Dirichlet is really a sharp theorem. So this theorem holds for all real numbers. And maybe you can improve it a little bit. One can improve it a little bit, but only by a little constant. And if you make your constant here a bit too small, then you already find the examples where the approximation claim is not true any longer. Okay, I just want you to keep this option sort of in your mind. We could call such a number badly approximable. If alpha satisfies this lower estimate instead of this estimate, then alpha is called badly approximable because it's not so good approximable. And one could argue that this is the reason why the golden mean actually appears in nature, because it is sort of a special number, because it's one of the worst approximable numbers. Anyway, so what is the theorem of Margulis about? This is a theorem concerning quadratic forms. I apologize for the slides already now. It's the worst one. After that, we'll have easier slides, more pictures, and so on. And also don't worry too much about, you don't have to read everything that's here. So the theorem of Margulis is about Oppenheim's conjecture in the area of the Diophantine approximation. What is Oppenheim's conjecture about? It's about a quadratic form in 3 variables. What is a quadratic form in 3 variables? I don't give you the general definition. I just give you examples, and by seeing examples, you know what I'm talking about. So the first example here would be just, or let's look at this example first. I have 3 variables, k, l, and m. And my expression that I'm looking at, this expression here, it's called a quadratic form in 3 variables. It's just, I take the square of the first one, I add the square of the second one, and I add square root 2 times the square of the third one. So that would be a perfectly fine quadratic form in 3 variables. Okay. Maybe the signs are different, maybe I have different coefficients, maybe I have some mixed terms, k times l, that would also be allowed. That would all things like that, all sums like that with only powers of 2 and products of 2 variables maybe. All such examples would be examples of quadratic forms in 3 variables. Now, I chose these 3 examples because they show what can go wrong if I want to look at small errors. So just like in the example here, I'm sort of trying to get small numbers for some reason. This is what the Oppenheim's conjecture is about. I want to get small numbers of this expression, of this quadratic form. Now, if I have plus k squared, plus l squared, plus square root 2m squared, then it's very hard to imagine to get this to become a small number, right? Because all the 3 expressions are positive. And I'm thinking of, I didn't say that before, I'm thinking of k, l, and m to be integers. So they're at least 1 big or even bigger, right? And if I now look at the squares, the signs go away. -1 squared is +1. And if I sum them up, I get definitely something that's bigger than 1, unless all three integers are equal to 0. That's always allowed to happen. I'm not interested in that case. I want to get small numbers, but not by plugging in zeros. That's not what I want. Okay, so here I have no chance to see arbitrarily small values because the sum will always be bigger or equal than 1. Okay, so here in this example, something else is happening. If we look at k squared plus l squared minus m squared, but without any coefficient sort of distinguishing the three here, then the square of this integer, k is an integer, the square of the integer is an integer. I add the square of another integer, I get another integer. I subtract the square of an integer, I get another integer. So this parenthesis here will always be an integer. And then I multiply this by alpha. Alpha is some fixed coefficient that maybe is the same coefficient for all of them. Then this expression will always belong to alpha times the integers, which is just this set consisting of all the multiples of alpha by integer numbers. And okay, alpha, I don't quite know how big alpha is. Maybe it's 1/10, but it's a fixed number. So if alpha is 1/10 or something, then between 0 and 1/10, I will not have any values of this quadratic form. So again, I'll not get arbitrarily small values. The third counterexample where you will not see arbitrarily small values is a bit more tricky. It relates to this badly approximable discussion here, because if your quadratic form is just somehow in a fake way a quadratic form of 3 variables, and really it's more or less a quadratic form in 2 variables, like this example here. So if I look at the difference, k minus l squared, but here it's k minus l in parentheses, and that's sort of one variable. If you look at this difference and subtract alpha m squared, then in some sense, I really have just one variable here. And with two variables in total, and with 2 variables, it may be that this is never getting small. Okay, so that's related to the previous discussion somehow. If alpha is badly approximable, this will never become a small quantity. So what I'm trying to say with this slightly too long slide is, if you look at the quadratic form in 3 variables and you want somehow small values of this quadratic form, there are 3 ways in which this can go wrong. It could be that your quadratic form is positive definite. You're summing just positive things. This is called positive definite. It could be that your quadratic form is a multiple of an integer quadratic form, and then somehow there's discreteness in the values and you will not get small values of the quadratic form. Or it could be that your quadratic form is somehow degenerate and is a quadratic form in really just 2 variables. And when this happens, then it depends on the coefficient somehow and is more delicate, and then you may not get arbitrarily small values. So to summarize, there are 3 things that can go wrong if you're looking for small values of quadratic forms. And Oppenheim's conjecture is precisely saying, suppose you have a quadratic form in 3 variables or more that is non-degenerate. It really is a quadratic form in 3 or more variables that is indefinite. It's not positive definite, not negative definite. So it has mixed signs, like this example has a plus and a minus, and this example has 2 pluses and 1 minus. So it's indefinite if it has sort of pluses and minuses built in. And it's also not a multiple of an integer quadratic form. If the quadratic form satisfies these 3 things, then the quadratic form takes arbitrarily small values. So that's Oppenheim's conjecture. He phrased it even a bit weaker than that, with 5 or more variables, and then Margulis proved it in 1987. And his theorem came quite as a surprise to the experts and relied on dynamical ideas. And this is where I want to go sort of next. I want to talk a little bit about the dynamics that goes into this proof and that Margulis really pushed and has become a very active area of research. So this is about the dynamics on the space of lattices. So omega d is the space of all lattices in d-dimensional Euclidean space. So here I wrote it down a bit more mathematically, how we would write it down. Lambda is a subset of R to the D, of this d-dimensional Euclidean space, and lambda is a lattice in R to the D. I will not give you the formal definition. I will just give you again examples. So here are two very good examples to keep in mind. So one such lattice for d equals 2, for instance, is the square lattice, which is just denoted c squared, which consists of all the red dots here, where I draw the dots precisely at all points in the coordinate, in the axis, in the plane, for which the coordinates, both m and n, the x coordinate and the y coordinate, both coordinates need to be integers. And because they're both integers, somehow I really get only this collection of dots. And this is all the dots together somehow. They form one square lattice, one lattice S, which is one example of such an element in omega d. It's maybe one vaguer way of thinking of this would be, it's a perfect infinite crystal. So these lattices are perfect infinite crystals in some sense. And this perfect infinite crystal could be really square-like, so that we have just squares, one square after the other, or they could be sort of hexagonal-like. And that's a different example of a perfect infinite crystal, where you really can sort of tile the whole plane in terms of these hexagons. And what you get when you do look at this example is, maybe you call it the hexagonal lattice, or you could call it the honeycomb lattice, because that's how the bees, of course, build their houses. So those are just two examples of elements in omega d. And maybe this helps you to understand a little bit what I mean by the space of lattices. The space of lattices really contains all such examples. Okay. And what's the dynamics about? So, for instance, I could think of three fundamentally different dynamical systems, if you wish, that I can perform on such lattices. And there are even more than that, but maybe those three are sort of interesting and I want to highlight them. So, for instance, you could just take a lattice and rotate around the origin, rotate the lattice around the origin a certain amount, a certain angle. And this would give you a dynamical system that mathematicians could study, except that this one is maybe just a bit too easy. We don't really study it that much because it's way too easy. For instance, we heard a bit of this recurrence being a theme in dynamics. If you're just rotating, of course there's recurrence. If you rotate by 360 degrees, you have rotated by the full circle and then you're back where you started from and you're not surprised by that. So it's not an interesting statement. Okay. Another thing you could do is you could do a hyperbolic stretch squash, by which I mean you look at the lattice, maybe start again with the square lattice, and then squash the x coordinate a little bit of all points and stretch the y coordinates a little bit of all points. And that is a much more interesting, much more chaotic dynamical system. In some sense, everything here is possible. This is really chaos as it is. And it's also interesting because we heard a bit about the history of ergodic theory and how it all came about. And I had to look up the name again. There was a paper that Emil Artin wrote in 1924. And the paper is called Ein mechanisches System mit quasi-ergodischen Bahnen. And it's really interesting because it concerned really this kind of dynamics And it was a paper that sort of gave this example even before ergodic theory was fully formed and really developing into a subject on its own. So this type of example is a very fruitful and important type of example that has been studied a lot since then, also by Margulis. Okay, but I actually want to focus on the third type of dynamics that you can envision, and that would be sort of shearing. You could say everything that's on top of the x-axis up here, I'm shearing to the right. And if something is much further up, then I would shear it to the right at faster speed. And if something is below, I'm shearing it to the left. And this kind of shear is sort of also an interesting dynamical system, but it's kind of a bit more tame. It's more understandable in structure, and it's also something that a particular dynamical system that Furstenberg studied in very influential papers earlier on. And one of the theorems, the second theorem that I want to mention of Gregory Margulis, concerns precisely this type of shearing dynamics. Okay. Before I want to state the second theorem, I need to explain to you that the space omega d, the space of lattices, is not compact. Okay. What could I possibly mean by that? Well, I mean that when I try to draw a picture of the space of lattices, then I obviously fail, because I'm thinking of d being 3 or 4 or something, and I didn't tell you the dimension of this space. It's actually d squared dimensional. So even if d is 3, this is a 9-dimensional space. And if I attempt to draw this space, well, I obviously fail. But even if I still want to try, and I want to get at least something right. So I want to get right that it's not sort of a finite space. It's not a bounded space, just like our world would be. The whole Earth is sort of a finite world. This space omega d is, for d equals 3, 9-dimensional, and it sort of stretches off to infinity. So that is an important aspect of this space, and that is what I mean, that it's not compact. It sort of has this tendril somehow that stretches off to infinity. And how does this come about? Why does it sort of stretch off to infinity? This I can understand when I look at the square lattice here. So here's my square lattice again. And I want to tell you what happens when I apply this stretching, this hyperbolic stretching map. Now, a squashing stretching, right? So I squash in the x-coordinate. So this point goes maybe here in the beginning, here. This point goes here, it sort of goes further up. And then I have this point, and here I have a couple other points. So what happens is that after applying this squashing stretching, the square lattice becomes a more rectangular lattice, where one side length has become much smaller. So this side length is much smaller. The other side length has sort of stretched. And in some sense, what's happening here is that I see a short vector. So this vector is now rather short. So maybe it's some element that is here. So I moved from the square lattice via this geodesic, via this hyperbolic squash stretching map. I moved somehow to here. And I can imagine doing this again and again, applying the same map again, which sort of squashes the x-coordinates and stretches the y-coordinates. And when I do that, what happens is that these points sort of disappear because they move further down and further up. But the points on the x-axis, they become sort of much more, they become much closer together. And I get points that are very, 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 many points that are very, very close together, which would correspond to a point maybe out here. So if I applied this squashing stretching map again, I sort of walked from the square lattice off to here. And if I keep applying this map, I just walk out here and never come back. And these lattices out here, they have precisely sort of very short lattice elements. They have elements that are very, very, very small, very close to the origin. In some sense, what's happening is that this approaches, in some sense, the situation where more and more of the real axis is sort of filled out, and outside of the real axis, I see less and less points. The next points that I would see will even be higher and higher up. So the limit, the thing that I'm converging to, the limit is not really a lattice, it's not in my space. So it's sort of, I walk off to infinity in some sense. Now, this is what happens with the squashing stretching map. The other thing that can happen, the other thing that I'm interested in is this shearing map, where I take everything and sort of shear to the right if I'm above the x-axis, and I'm shear to the left if I'm below the x-axis. And what happens is that, okay, I shear while now I have my point here, for instance, and this point moved here. And then I just walked a little bit and I'm at a different point in my space of lattices. But if I shear even further and this point actually moves all the way to that point, then I actually end up with the same square arrangement of lattices that I had before. So in the space of lattices, what this means is that I'm walking and then end up where I was. So it's like, it's just a periodic point. So this is just a periodic point for the shearing map. So maybe you can see from the two pictures that the squashing, stretching operation is really very, very, very different from the shearing transformation. And what Margulis showed, 1971, is that if you do the shearing dynamics, and no matter where you start at some omega in the space of lattices, there's always some fixed, bounded, compact piece. Maybe I draw here a line and maybe say this is my K. So this is a bounded part of my space of lattices, my omega d. And I'm starting my dynamics. And maybe when I walk around with the shearing dynamics, I never walk out of K. That could happen. And the conclusion of Margulis' theorem would be perfectly all right with that scenario. However, it may also be that the shearing dynamics walks out. But if it walks out, it actually walks back again. So not like our geodesic, our stretching, squashing dynamics that can walk out and never come back. The shearing dynamics always has to come back, do something maybe, and then walk out again, and then come back again and walk out again. Eventually it can walk out further, but it will always come back to this compact set. So there's a definite promise that there is recurrence to this large set, large but bounded finite set. And that theorem sort of became a cornerstone, and it was refined and applied by many, many, many colleagues and students and collaborators of Margulis later on. It really became, so Dani refined this statement in a particular way, and this refinement became a basis of quite a bit of homogeneous dynamics, how it is called now. Okay, I'm slowly running out of time, but maybe I want to just mention that the proof of Margulis' conjecture actually used more or less the space of lattices in 3 dimensions also, with a slight ornamentation. He studied the lattices that had co-volume 1, where the one building block of this crystalline structure, 1 billion block, should have volume 1. So maybe the square and the hexagonal lattice we can normalize so that the square has precisely volume 1, or there's a parallelogram that should have volume 1 in the hexagonal case. And what's kind of amazing, if you haven't seen this before, is even for Margulis wants to prove a statement for a real number for just 1 dimension, it was actually better for him to prove a different statement, a stronger statement in this 8-dimensional space, because this 8-dimensional space has more structure than the real numbers, and it carries a dynamical system related to quadratic forms and related to Oppenheim's conjecture. So by that, of course, was just the bridge, but or maybe that was the starting point of the bridge to actually then completely prove the theorem. He had to prove a very difficult statement at that time for this dynamical system on this 8-dimensional space. And this proof became a precursor of Ratner's theorems and has had tremendous impact on mathematical research in the last 30 years concerning this interaction between dynamical systems and number theory. I want to mention just two more achievements of Margulis that came about roughly around my birth. So in 1973, Margulis constructed the first explicit expander graphs using Castan's property T. And that sort of built a bridge between graph theory and computer science and harmonic analysis for simple groups. And it's really, if you didn't see that before, you should be amazed, because graph theory, that's sort of talking about things like, yeah, we have sort of vertices and then they are connected to one another maybe. And this is the theory of such objects is called graph theory, and it connects to computer science because each things here, each node could be precisely a computer, and the edge could be precisely, we have built a cable between those two computers so that those two could communicate. And this is one side of the story that was connected. The other side is harmonic analysis, and harmonic analysis is about waves in some sense. But yeah, there's this mysterious for simple Lie groups here, so it's a more general wave discussion. And Margulis found a connection between those two things and was able to give an expander graphs, which are sort of sparse. Sparse is a good thing because you don't want one computer connecting to all the other computers in the world. That's not feasible, that will never work. You can only connect your computer to a few other computers. So there's some upper bound on how many connections at a particular node can be made. And on the other hand, you want your computer to be connected, or I want my computer to be connected to your computer without too many computers in between, right? So I want some connectivity of the whole system. And that's what expander graphs are about. And I also find quite amazing the proof of arithmeticity, but really that would lead us now a bit too far. So I think I'll stop here. Thank you for your attention.
Thank you very much, Manfred, for your very nice contribution, illustrating the power of dynamics in many deep mathematical problems. And I would also take this occasion to thank actually all the speakers, that means Charlene, Benjamin, and Manfred, for their contributions. Explaining deep work is quite a challenge, and we appreciate it very much, your clarity and very beautiful explanations. So now I will give the floor to Professor Frank den Hollander, who will moderate the discussion.
Yeah, thank you very much, Frank. Yeah, there's been some interesting discussion going on in the question and answer session. There were several questions that were posed to Charlene, and she had all the opportunity to provide answers to that written. That was nice to see. I would like to ask a very general question to both Benji and Manfred. I mean, Frank Redig started by showing a bridge, and if you indeed look at the work of these two fantastic mathematicians, one thing that strikes you all the time is their enormous capability of translation. I mean, if you see what Hillel Furstenberg did, you talk about a problem, and then he suddenly puts it in a completely different setting and out pops something remarkable and beautiful. And also in the work of Margulis that Manfred explained. You see these incredible twists. So maybe I can invite both of you to sort of comment on that particular capability that will open doors. This is one of the most fantastic things that a mathematician can do, is to use this skill of translation and seeing things where other people have not seen before. So I would invite both of you to comment on that particular feature of both these Abel Prize winners. So Benji or Manfred, will you unmute?
Yeah, it's very difficult to answer that, because I totally agree with what you said, that it's an amazing talent that some of us have, or the best of us have. The best of us mathematicians really find these insights that, even though maybe this works differently, and maybe the experts from this area speak a completely different language than the experts in this area, and some of us sort of really manage to learn both languages enough to understand that behind the scenes we are talking about a related, or maybe even about the same object in a secret manner, and then one can use this to the advantage of sort of pushing statements from one side to another. And yeah, it's an amazing talent. I don't know what else. Maybe Benji, you have more insights.
Frank, can you let me start the video somehow?
Okay. Yeah.
You are asking me to explain the inexplicable.
Yes, I did that on purpose.
I mean, I have no, you can't explain genius. I mean, at least perhaps some psychologist can make a study of this, but I mean, connecting things which on the surface are not connected, making unexpected connections. This is creativity. This is creativity. I mean, mathematicians come in many variety. There are varieties of mathematicians who can do great technical work, who can perform long and difficult calculations. For example, the construction of a group with an unsolvable word problem. I mean, this requires a very lengthy formal calculation, but not some insight connecting suddenly, bringing some tool from some other area to bear on this problem. I mean, there are some mathematicians who can make these unexpected connections. There are others who develop, who have a great technical ability. There are people who solve problems. There are people who ask questions.
Yes.
There are many varieties of great mathematicians. I mean, I haven't had many students. I had a student who could do calculations which I found difficult to follow, but he proved beautiful things. I had a student who had great ideas, but he needed help with the technical details. He had great original ideas, and I helped him with technical details. I mean, it's...
Okay, that is Yeah, I agree.
Maybe to some extent you're asking, how do we find gems, right?
Mhm.
Well, you need to have good eyesight, so you need to be close to a genius or something, and you really have to dig a lot. I mean, there's hard work involved, and there's the right eyesight needed to find those gems. And even then, I think they remain gems. I mean, they are not sort of found on the street. It's something something unexpected happens not every time, right? Of course, they did happen often in the work in the lifetime of Margulis, and I think they also happened often in the lifetime of Furstenberg, life achievement. So those are impressive collective works.
Can I ask you another question that is sort of linked to this? Of course, two extremely brilliant mathematicians. Do you I mean, do you notice also some personal qualities that made a contribution to their success? So were they also very capable of interacting with the people around them and you know, and pick up everything, or was that did that not play a particular role?
Well, I know Grisha, but I don't know him very well. I know Hillel very well. And as a person, I mean, I didn't say anything about his modesty, his goodness. I didn't, I wasn't going into his personality. I think that in spite of the fact that he worked extensively. I mean, during the years when he was working with Izzy, I can tell you that they would spend hours daily talking to each other. I mean, it was not a collaboration where Hillel would sit alone and Izzy, I mean, they spent a great deal of time. My personal collaboration with Hillel over the years has always involved many, many, many discussions. We would spend lots of time together, and he would often come back with some insight, and that would push the work forward. I mean, I can't compare his style of work with that of Grisha. I don't know him well enough.
But there again, Benji, what we'll be counting is that there are many different types of way of doing it, and as long as you do it well, it will bring something very interesting.
Yeah.
I also think that nowadays we see way more collaborations than we did see sort of 50 years ago in mathematics, because I think the experts were really more isolated, so they really worked more by themselves, and occasionally they met. And I think that's why many of the works of Margulis that I mentioned are single authored. And nowadays I think it's way more common that, since it's so easy to talk to someone regularly, even though we live on different continents, it's much more common today than it was back then.
It's become a very global science, mathematics, and communication has been easier. It's 8:30. I want to close this session. Thank the three speakers and also the two organizers very much for making this event possible. I also want to thank the people of the KNW who have been supporting this, and I wish everybody who attended this KNW webinar a good continuation of the evening. So thank you all very much.